Hello learners, welcome to NeenvIAS. This is our session on concept behind current affairs and the topic is top quark. The topic is top quark. So let's learn. See, this was in news and the Hindu article that was reported said, why are scientists looking for Higgs boson's closest friend? So the question is on closest friend. So we will learn about Higgs boson, we will learn about Higgs field, we will learn about the best friend or rather closest friend, that is the top quark, right? So that is the main part of our learning today, right? Before beginning anything, we need to understand what are fields. Now fields are everywhere, right? In the universe, according to quantum physics, fields are everywhere, and you and I and every planet, every star is affected by these fields, right? And we all are made of particles, and every particle in the universe is affected by these fields. Now these fields are of different kind, and whenever particle interacts with this field, the particle gets some property, and we are going to focus on Higgs field, right? So we all are made of particles, and when the universe began, there was no mass in any particle. Every particle was massless, but slowly when they interacted with Higgs field, every particle started getting some mass according to the interaction it was having with the Higgs field, right? I have explained this. And in fields, whenever there is some excitation, that means if something is happening in the field and there is some interaction in the field, a particle will be produced. It is called excitation. For example, in Higgs field, the excitation is Higgs boson, all right? And in the electrical field, the electron is the excitation of the field, all right? So Higgs boson is Higgs field excitation, electron is electron field excitation, right? So we are coming to Higgs field because we are going to focus on Higgs boson and the closest friend, the top quark. So in Higgs field, the thing is, Higgs field is the field that gives mass to particles, which I've already mentioned. Now the mechanism exactly we don't need to go into detail because that is not in our syllabus. But we need to understand that there is a Higgs field and Higgs boson is the excitation. All right. See, if there was no Higgs field, this is very important, because if there was no Higgs field, there will be no mass and things won't exist as they exist right now. Our world would completely be different if there was no Higgs field. So remember, if there is any question on this, you will have to tick mark something like it will change the whole universe. Remember this, it is such an important field. All right. Now, a particle has mass, right? We just discussed this. Every particle that exists has some mass, and there are few exceptions, right? So every particle basically for our purpose has mass, and the mass in the particle is given from different fields. Just like we take blessings from our parents, from our elders, right? From let's say religious figures in respective cultures. In the same way, the mass is given to a particle from different sources, but the major one is the Higgs field. It gives the mass to the particle, and this is applicable to every particle in the universe. All right. Now, whenever the particle interacts with the Higgs field, so the field is everywhere, it permeates the universe. There is no place where the field is absent. So whenever the particle interacts with the field, they experience a drag. All right. Imagine you are walking, right, and there is no resistance. In real life, let's say you are walking down the road on a normal day and there is no wind, nothing. So you will feel minimum resistance towards walking. But if you enter let's say a swimming pool and you start walking in it, you will experience some drag, right, some resistance. Similarly, if you try to walk through mud, you will also feel resistance. So that resistance, you can imagine, is felt by every particle whenever they are going through Higgs field. I hope that is clear. So this drag that a particle feels, it is the mass. All right. This drag is the mass that is given to the particle. I know it's a confusing thing, but quantum physics works in a very different way, and we just need to understand the concepts by examples. So that's why I've given you example of swimming pool, mud, and walking normally. So the drag is the mass. All right. Drag is the mass. Now this mass is not given equally to every particle. Now what do I mean by this? See, the thing is, more interaction with Higgs field leads to more mass in the particle. If the particle is not interacting in a, let's say, if the particle is not interacting in a, let's say it's not taking a lot of time in the field, then it will not have much mass. So smaller interaction leads to lighter mass, longer interaction leads to higher mass, right? Okay. For example, photons do not interact with the Higgs field, then no mass. Other particles like electron, quarks, and bosons interact with the field, hence they have different masses. And remember this relation: more interaction, more mass. All right. Now, in 2013, a Nobel Prize was given to Francois Englert and Peter Higgs because they explained how this mass was given to the particles. This was a great mystery to everyone, because how did mass came about in the universe after the Big Bang? Everybody was trying to find out, and finally they cracked the proof. It was theorized in 1970s and 80s, but they actually showed how it is done, right? Let's move ahead. If you see this image, it will give you a pictorial representation of how things work in the Higgs field. So there is a matrix like pattern in space, right? Just imagine that as a field, although we don't see it this way, but we visualize it this way so that we can understand things. Now a quark is going through the field. Now it is interacting most with the field in terms of other electron, let's say the electron and the photon. In this example, it is interacting in the biggest manner, right? So you can see the depth or the bend in the fabric is more, but if you see electron, it has less bend. It has less bend as compared to the quark. All right. And finally, the photon is not interacting at all, right? So this tells you that the amount of interaction with the field will lead to the amount of mass acquired by the particle, right? So quark, electron, and photon. Now we come to the next point, which is boson, right? To understand this, it's quite easy, but again, you will need examples so that you understand what these actually are, right? So bosons are force carrying particles of the universe. Force carrying particles, that means they don't produce force, they take it up and they carry from one place to another. So what does this make them? Don't you think they're like courier companies like DTDC, Blue Dart, right? So these are force carrying, they carry something from one place to another, and there are different types of particles in boson and they carry different forces, right? So let us see them now, right? So they are subatomic particles that carry forces, like I just told you, okay? So they are messengers basically, and let's say whenever two particles want to interact, the bosons will be let's say the coordinator between them. Particle A, particle B, they want to interact, and bosons will be the one bringing them together, right? Now the force can be anything. It can be of attraction, it can be of repel, okay? REPEL, repel, right? Let's see the examples. Higgs boson help in carrying the mass, photon is of the light, right? And gluon, they carry strong nuclear force between particles, right? So just these examples are enough, and they carry the forces. Remember this. If you want to understand the analogy, like I said about DTDC and all, and another example, you can imagine them as post offices, right? Now we come to the Higgs boson. We just understood boson, we have understood Higgs field. Now you will understand this particle. Although I have already told you that Higgs particle is the excitation of Higgs field, right? Higgs field and its excitation is called Higgs boson, right? So it was proposed in 1964 by Peter Higgs, hence the name is Higgs, and 5 other theorists to explain why some particles have mass, and its existence was proved at CERN in 2013, and this was a very big news then, right? Now function is it carries the force. Why? Because it's a boson. I've already explained a lot of things, so I'm just reading them out and discussing together. So it carries the force, of course, right? Now mass accusation, I've told you whenever a particle interacts with Higgs field, there is an excitation of the field, and during the excitation of the field, a particle is produced of the particular field, and that particle is Higgs boson, and that will carry the mass and it will be given to the particle. So I'll bring it all together, don't worry. So for example, quark is traveling through the field, and whenever the particle is traveling, it will excite the field. All right, now that excitation will lead to creation of Higgs boson, and that boson will give the mass to the quark. Now this is in a very simplified way, in a very non-technical way. All right, don't go into technical details because it is not at all required for UPSC. That's the beauty part. All right, now Higgs boson, you can call it in another way, you can define it in another way, which is it's the smallest packet of excitation of Higgs field. So it is the smallest detectable packet of the Higgs field, right? So if a question comes in this way, then please don't mark it as a wrong option, right? You have to mug this up, this property, that is scalar boson. It has zero spin. Now spin, I'll briefly discuss it because it's not relevant here right now, but the spin means it's a property of a particle, of a subatomic particle. Now it does not mean the spin that happens like this. Okay, so this physical spin is not the real spin, sorry, this physical spin that I just did, it's not the same for the quantum particle. This spin is different. It's a property which tells some angular momentum, and then again it is also a different thing. So we are not going to go into depth, just understand that it's a property of a quantum particle, and whenever it is written in particle physics, it's not spin like a merry-go-round or a circle. Okay, so zero spin, remember this. So what is the significance? See, its discovery confirmed the existence and properties of Higgs field, and it explained that yes, mass is given. Mass is not something which is present from the birth of the particle, it is given later on, right? Yeah, please remember, if they carry the mass, they don't give the mass. Okay, it is given by the field, right? Now this is an interesting question. See, is it really the God particle? Remember this thing, the story, obviously I'm going to give you the answer, but I have brought a little story for you because it helps you remember the reasoning. So what happened was, there was a Nobel laureate, right, Leon Lederman. He was writing a book on this particle, right, and it was before it was confirmed, when it was only theorized. See, this particle is very hard to detect. So the problem was, Mr. Leon, he said that this particle is so hard, you know, goddamn particle. So basically, goddamn is, let's say, it's sort of a, let's say, negative word towards something, right? So goddamn means we can't find it, you know, and it's a negative word. In a funny way, he was saying this. So when he was writing his book, he wanted to name his book on this particle as the goddamn particle. But the publishers changed this and they named it as the God particle, right? So the physics fraternity or the physicists, they don't like this particle being named as God particle. They don't support it, and it is also not a God particle, right? So this is a story behind this, and please remember, it's not the God particle, but media and the because of the book, the media made it so, and then it got famous because of this name. Okay, so I hope you understand this. All right, now let us understand, like I told you, I'll bring it all together. Let us now understand by one analogy. I have another photo for you. We'll discuss that down the line. So remember this analogy, it is a let's say a standard analogy given for this field, Higgs field. Okay, the cocktail party analogy. Let's say many people are in the party, right? Many people are in the party, some are interacting, some are not interacting, and there is a famous person over here. Now whenever a famous person comes to a party in real life also, right? So whenever a famous person comes to a party, everybody huddles around them, everybody goes around the famous person, and they want some seconds of interaction with the famous person, right? So everybody goes around the, or rather collects around the famous person. So now these particles, now these are Higgs particle. Okay, these are Higgs particle, they collect around this another particle which is interacting with the field. Now this interaction is leading to mass generation because lot of particles are now collecting around Mr. Popular. So let me explain it again. Now I am not going to take example of Mr. Popular or something. I'll explain it in our topics terms, right? So imagine this is the Higgs field, lot of particles are there. Now there is a particle that is coming into the field, and then it starts interacting, and other particles come around the incoming particle. Now if this particle interacts a lot, it will gain a lot of mass. If this particle does not interact a lot, it will not gain a lot of mass. We know this. So if the particle interacts a lot, let's say this is a lot of interaction, so it will gain a higher mass. So this is how you can imagine the mass generation of a particle. Okay, let's move ahead. Now we come to the next topic in this session, quark. Now quark, basically I like to give an analogy here. Even 2500 years ago, the Greeks were discussing, and there were few Greeks that were discussing what is universe made up of. One of them said that if you break down everything, it will result into air, water, earth and fire particles, right? But slowly in the last 200 years, we have realized that atoms can be broken down into different things, right? Like the electrons, protons and neutrons. But even after that, recently it was discovered that, recently in the sense last 20-30 years, which is small time in physics discoveries. So in last 20-30 years, it has been obviously theorized and discovered that even the protons and neutrons can be broken down into further particles, and the quarks are them, like quarks are one of them. So quarks also they make up, let's say, the proton and the neutrons in the nucleus. So a cell, right, it has an atom. Every cell has an atom, right? And that atom has proton plus neutrons in the nucleus and the electrons, right? And these two have, or basically these two are made of quarks. All right, so this is how a distribution goes in real life. So these are elementary particles, that means they cannot be broken down into anything else, right? So electrons are also elementary particles because they also cannot be broken down into something further, but protons and neutrons can be broken down, right? So they are building blocks of proton and neutrons, right? And there are 6 type of quarks: up, down, top, bottom, right? And then strange and charming. So there are 6 flavors or 6 type of quarks, and they have different properties, different mass, right? Another fact that I want you to mug up is that quarks are never found in isolation in the nature. They are always combined. All right. Now that is again because of their characteristics. Now don't go into depth here, but please remember this. Okay. Let's move ahead. Now here you can see proton and neutron. there are up quarks and down quark, 2 of the 6 flavors of quarks, and it is made of 3 quarks, right? And this is also, but here are 2 down quarks, here are 2 up quarks. This is also something which you can just understand. If you want to mug it up, you can mug it up, although this thing, it has very less probability of being asked, but this is important for understanding, right? This visualization is always important. Right, now the topic, initially I told you, right, we are going to discuss top quark, and this is the headline of the lecture. Now, all of the explanation is building up to understanding top quark and the relation between the Higgs field, right? So it was discovered in 1995. It is the heaviest quark known to us, right? It is heaviest subatomic particle. It is the mass is 172.52 giga electron volt. Don't worry, I'll explain why it is so huge, and we'll also see the giga electron volts, right? So if we compare it with other particles, it is 10 times heavier than a water molecule. It is 3 times heavier as a copper atom. It is 184 times the mass of a proton, and it is 95% heavier than caffeine's molecule. Okay, now there are some properties which is very important to understand, and there can be some tricky questions that can be created on these lines, because in 2024 prelims UPSC has asked about nuclear energy and the lifespan of a star. So similarly, because this was in news and it is quite an important discovery in the universe, in the understanding of the universe, hence please understand the property. See, it has a short lifetime. It decays almost instantly into other quarks. Okay, so it is very difficult to measure. Secondly, it has a big relation to Higgs. Why? Because its interaction is quite large. Like I said, it is heaviest known quark, and I've told you before that if the mass is high, then interaction is also high, right? Next, most massive particle. Now this top quark is the most massive subatomic particle that is known. So these are the properties. It decays instantly, it has a very high mass due to high interaction, and then it is the most heaviest subatomic particle, right? Okay, let's move ahead. Now understand this figure. So these are molecules. Everything is made up of molecules, right? And this is an atom. Now every atom has electrons and a nucleus, and in the nucleus we have proton and neutrons, right? So let's imagine this as protons and neutrons, and this is the proton. So scientists were curious that why not these protons just run away? You know, why are they attracted to each other? Why don't they run away? Why do they make up such a strong nucleus and things like that? So why the particles are not running away into their own direction? Why are they not free to go anywhere they want, right? So they were curious about it. The researchers, let's say theoretical physicists, everybody was curious about this, right? So what happened was, they collided the particles in a particle accelerator. You can imagine the particle accelerator as a big highway, and just to understand, they collide two cars or two vehicles in order to break them and then understand what are they made of. So they collide particles at very high speed, like close to speed of light. So they collide the particles break, right? And then they try to understand what they are made of. And from there, they realized that Higgs boson exists, and that is the reason of mass of the particles. That is why protons have mass. Protons have mass. Sorry, I'm slightly not well today, right? So I hope you understand this chart. Okay. Next, we go to the mass energy equivalence. mass energy equivalence. Now this is briefly mentioned in the article, but we need to understand this because the relation between the mass and energy is crucial to understand any subatomic nature, right? So E is equal to mc square was given in special relativity by Einstein, Albert Einstein. So the equation is E equal to mc square. Now m is the mass of the particle and E is the energy that you can produce, and c is the speed of light, which is around 3 lakh kilometer per second. Now this equation says that you can convert any mass, right, into energy. And second thing, a small amount of mass can create huge amount of energy, because even a 1 gram of mass will be multiplied by square of speed of light, which is 3 lakh kilometer per second. So even a small mass can create huge energy, and this is what is used in nuclear reactors. A small mass of uranium creates huge amount of energy, right? So you can imagine this equation as a conversion rate, between energies and mass. Let's say there are dollar and rupee conversion rate. So the conversion rate will be E is equal to mc square in physics, and dollar and rupee can be the energy and mass, whatever you want to take. All right. So we have we have covered all of this. So this is important, and let's understand what the article says. Yeah, one thing is also there. Obviously, I talked about nuclear reactors, but sun's energy is also created in the similar manner. It converts mass into energy, and that energy reaches us in the form of heat and light, right? Now the relation given in the article is this. See, heavier the particle, the more energy, because of mass energy equivalence. Like I said, even 1 gram of mass can produce huge amount of energy. Now if the mass is huge, then of course the energy is also equivalently increased, right? And the top quark is the most massive particle discovered, hence it has the most energy also, with the most energy, sorry. And decay, now this is important. The more massive the particle is, the faster it will decay into the lighter particles, releasing excess energy. This can be a tricky question if asked, because you can imagine in real life what we see, the stronger person holds things tightly, but if a subatomic particle is massive and it has more energy, it will release that energy as quick as it wants or as quickly as possible and go down to a lower energy level. Now this happens a lot. Electrons also, when they have more energy or they get excited, they release that energy and come down to their normal energy. So this relation is important. Questions can be asked on this because it is confusing in nature. Now the next terms I want to discuss are MeV, mega electron volt, and GeV, giga electron volt. Now these are just units of energy, and why I want to discuss this is because till now I have talked a lot about the mass and energy, right? So now let us understand how big actually the top quark is. So if we see the particle, the mass is given in two figures and relative mass is the third column. So first mass is in GeV, that is the giga electron volt. It is 1 billion electron volts, and mega electron volts are 1 million electron volts. So remember the difference. M means million electron volts, G means billion electron volts. So the top quark, its mass was found to be 172.52 GeV, all right, GeV. So in MeV it is 172520. So basically 1,72,520. Up quark, that is another type of quark, it has 0.0023 GeV. So just imagine 172 and 0.0023. Next, electron in GeV has a mass of 0.000511. and Higgs boson has a mass of 126. That means just 126, right? So as you can see, top quark is closely related to Higgs boson rather than its own type of quark, right? Or rather its own sibling quark, right? So top quark is by far the most massive. This I wanted to show you, right? Let's move ahead. Now, yeah, let's come to the article itself. Now we have discussed all the concepts that were in the article and all the concepts that you need to understand so as to appreciate the article actually, right? So the article says, why are scientists looking for the Higgs boson's closest friend, and physicists have reported the most precise estimate yet of the top quark's mass. So top quark is the star of the article. Now this is closely related to the universe existence, hence we have to study this article properly, right? So let's come to the article, and the first thing I want to discuss is Higgs field and Higgs boson relation and the importance in the universe and why we have to read it in the article, right? So the mass of Higgs boson is at 126 GeV. Now this is very peculiar because the mass of mass of Higgs boson tells us the energy of the Higgs field, and scientists found out that the mass of Higgs boson is more than expected. So the electron field, the boson field, the Higgs field, right, that is also having more energy. Now this is of concern. This is important to understand because I think in economy you must have studied about stock market being overvalued, right? So whenever the stock market is overvalued, it will correct itself, right? There is a correction. There is a term actually called correction of the stock market where it decreases slightly, right? So similarly, scientists, especially Stephen Hawking, he was very, let's say, careful about this, and he said that if the mass changes, right, and if the mass changes, the world will change. Yeah, so he said that. I'll discuss that in the next slide. So the point is, this mass is very tuned at 126 GeV, and this keeps the universe in its current state. Any deviation, even if it decreases, even if it increases, anything up and down will change the universe as right now, and it will turn into something else. We don't know what it will turn into, but it will change, right? So why is the curiosity? First is the mass. They are very curious because the scientists, by they I mean the physicists, the scientists, they are curious because this the number 126 GeV is fixed, right? It's not changing, and somebody, or let not, I should not say somebody, but nature, the processes in nature made it at 126, and they're curious to find out why this number, why not 99, why not 299, why not 599, right? So first thing is there. Next, Higgs boson particle does not have mass of its own when it is created. Even the particle Higgs boson gets its mass by interacting in the Higgs field, right? So they want to understand also why Higgs boson has 126 GeV, right? Next, high energy, which I discussed already, right? The Higgs field which pervades the universe is more energy laden than expected because, see, Higgs field is proved by the existence of Higgs boson, and the mass of Higgs boson was found to be 126 GeV. So scientists have concluded that the mass that is provided by the Higgs field is high for Higgs boson. So Higgs field also has high energy. Okay, only then it will provide high energy to Higgs boson, right? So in future things will be found out, and scientists for now have theorized that Higgs field could self-adjust in future, but the probability is very less, right? So Stephen Hawking in 2016 said that Higgs boson could potentially lead to the end of universe. Now this doesn't mean that universe will be totally destroyed, it will just change, because currently whatever we see right now in our life, in space, in universe, that all comes from the mass, and mass is given by the Higgs field, and boson's value from Higgs field is 126 GeV, right? So if the strength of the Higgs field changes, the universe will change. I've already discussed this, but the probability is very less, 1 in 10 raised to 100 years, right? Now we come to the next thing in the article, which is top quark. Now, in the way that I explained the curiosity behind the Higgs boson, similarly, we are going to discuss the curiosity behind the top quark. So, why was it in news? Because on June 27, 2024, Large Hadron Collider physicists measured the top quark mass at 172.52 GeV, and this is the most precise value yet, because since it has been discovered, scientists have been trying to measure it, and of course they will try to measure it so that they can know its properties and all, but it is very short lived, like I have discussed. Hence, calculating its mass is very difficult. It does not even exist for even 1 second. It exists for almost 10 raised to minus 25 seconds, right? Something like this. So it does not exist at all for even 2-3 milliseconds. So it is very difficult to measure. Hence the importance of top quark's mass. So why it is important to understand? Because both of these particles, the top quark and Higgs boson, are extremely essential for understanding the standard model of the physics, which is the most popular model that explains our universe. There is also string theory, but we are not going to discuss them right now. Next is strong interaction. We know already, because see, Higgs boson mass is 126 GeV. This top quark's mass is 172, let's say approximately. So obviously, and we have already discussed this before, that this is the heaviest subatomic particle. So it interacts the most with the Higgs field. So even more than the Higgs boson. So this top quark becomes extremely important for us to understand the Higgs field. Okay. So it is also the closest friend in terms of mass with the Higgs boson. So I hope you understand the relation of top quark, Higgs boson, and the Higgs field. Next thing and the last thing about this thing, the quark, is peculiarity, because top quark, see, like I told you previously, that there are 6 flavors of quarks, and you could imagine this easily and you would not be wrong, that these quarks could have or should have, let's say, close number of, let's say their mass should be close, right? They should not be very different. As you can imagine, in a family also, if you have siblings, then they are closely related to each other. Your skin color might be the same, your facial features might be same, right? So these things are similar. We expect that in real life. So similarly, scientists were expecting this to happen with the top quark, but we will see what happened. So this is the last peculiarity, and this is very important. So let us see the third peculiarity. The top quark is closest in mass to the Higgs boson rather than its own siblings. So the quark and the mass. So up quark is, see, one thing I'll tell you before everything. The first 4 that I have written, they all are in MeV, and the last 2 only are in GeV. Okay. Now let us see the particles. See, the up quark is 1.7 to 3.3 MeV, down one is 4.1 to 5.8, charm quark is 1270 MeV, strange quark is 101 MeV, top one is 172 GeV, the focus of our article, bottom one is 4.19 GeV, and till 4.67 GeV, there are different types, right? So the thing is, like I said, in a family, people are closely related in features, but this master top quark is totally different from some other arena, and it is 172 GeV, the highest subatomic particle, and nowhere closely related to its siblings, right? So the peculiarity is the top quark is more closely related to Higgs boson as a particle rather than its own family, right? Okay. So the last thing which I want to discuss is Higgs field and the mass. See, just briefly recap in just one line. So Higgs field gives the mass, and the interaction, the amount of interaction or the strength of interaction determines the mass, right? So what is the challenge with top quark? See, it has high mass compared to other quarks, and this defies the expectation. Like I said, the first thing it did was it changed and it defied our expectation. We were expecting it to have similar mass to its siblings, but it did not, right? Next is the doubt now it has created in the minds of physicists that there is something different now. Okay, it did not go according to our expectations. Like I've discussed in dark energy and dark matter session, scientists were trying to observe the universe. They found something which challenged their notion of current understanding of the universe. Basically, it challenged their current readings and understanding. So they theorized that dark matter or dark energy exists. Similar thing is happening here. They expected top quark to have some similar type of weight or mass with respect to its siblings, but that did not happen. So physicists are saying that something is missing, or the Higgs field interacts very differently with the top quark, right? So something is missing. Okay, that is the main point. So basically, it is beyond the standard model. This is one option. Also, it is an oddball particle because of this, because its mass makes it unique particle because it does not relate to its siblings, right? So this is the thing. So we are done with this session. So just to briefly recap, we saw each of the concepts like what is quantum field, what is Higgs field, what is Higgs boson. We saw what is a quark, what is a top quark. We understood the E is equal to mc square relation of special relativity, right? We understood the article, what the article found out, and what are the implications of the findings, and the implications were discussed in the terms of peculiarity of both the particles, Higgs boson and the top quark, right? So that is all for this session. Let me just confirm. Yeah. So that is all for this session. Thank you, students. I hope you learned something. Please do revise, right? That is the most important thing in this exam. All right. Take care.